Hi everyone, today I would like to talk about the average, variance, and expected value. This is the third video in this video series I have for numerical linear algebra and optimization. The purpose of this video is to connect some of the concepts used in the optimization and numerical algebra textbook to the concepts used widely in probability. So for numerical linear algebra, in most of the textbook, there is no need for to have a background in probability. But I believe if you have background in probability, you can grasp the material much better, and you can actually find or prove the more generalized version of the theorems that you see in the more basic linear algebra textbook. So this is the point of this video, to actually be a gateway between the probability and concepts used in the numerical linear algebra. So let's start. I'm gonna start with definition of the probability. So probability, there are two definitions for that. One of them is a relative frequency of an event in a long run. This is a frequentist approach. This is a frequentist school of thought. The second one is the uncertainty or belief in a real world. Measure of uncertainty or belief in a real world. This is a Bayesian definition, right? Okay, I have a video actually about Bayesian versus frequentist estimation. I talk about the Bayesian versus frequentist approach to the probability. I will put a link to the description. It's not necessary for this series of video, but if you want to know more about that. Now, about axioms of probability. First, probability is bounded between 0 and 1. So probability of an event can be as low as 0, means that it never happens, or can be as high as 1, means that it surely happens. It happens with probability 1. It always happens, right? Probability of sample space is 1, right? Sample space is a set of all possible outcomes. So sample space always happens, right? And let A and B to be two events. Right? Then probability of A or B, this is or union. Probability of A union B or A or B is equal to probability of A plus probability of B minus probability of A and B, right? So this is usually intersection, and it's something denoted like this as well, right? So this is the axiom of probability, very fundamental, and are used in a definition of probability to compute the probabilities, especially the third one actually is pretty important one. Okay, now after probability, we talk about the random variable. So random variable is nothing but a mapping or the function between elements of a sample space, right, to a real line, right? So element of sample space, let's say denoted by W1, W2. So this is a sample space. This contains like W1, W2, all the way to Wn, and you map it to the real line. For example, when you toss a coin, the sample space is head or tail, right? You go ahead and say that, hey, I want to map head to 0 and tail to 1. So this is a random value. Define random value x to be 0 and 1, right? So you can do it for actually any event. Now, and this is what I have, definition of the domain and codomain. Remember in the last video I defined the function. So this is the domain is an element of sample space, and the codomain is the set of all real numbers. Okay. So now there is a concept used very widely in probability and random variable. It's called expected value. Expected value in a simple term is called is the mean, is the average, right? But more generally, if x is the discrete, is defined as mu of x, or mu is the notation used for the mean, like x equal to expected value of x equal to the summation, if x is discrete, each x times the probability that it can occur, right? So it's called PMF, probability mass function, right? For example, in toss of a coin, you want to find the expected value of these, you calculate them, you will say that x is like 1, is like for probability of less than head, has probability that head occurs, and plus 0 times probability the head occurs is like 1/2, right? So expected value is equal to 1/2. And there's no surprise because this is an example of a Bernoulli random variable which expected value is equal to P, probability of success. But we don't care about this sum. This is not a course in probability. It's just to talk about some important concepts and relate them to a concept we will later on see in numerical analysis. Okay, now if x is this continuous, we will not have any PMF because it cannot take a certain values. So if x is a continuous random variable, the probability that it's equal to a certain value is 0, right? So in that case, we define a PDF, probability density function. What is PDF? So I defined the PMF here for you guys, probability mass function, and I will go over this example. Well, let's first define the PDF. Probability density function is a probability that this random variable x is between the little x and the little x plus delta, right? So we define the continuous random variables in an interval. So this is a graph of the f of x, the PDF versus the x, and this is the how you can actually visualize that. Okay. Now, for this expected value, when you calculate for a continuous variable, you just change the PMF to PDF. The notation P is changed to F, and the summation sign is changed to the integration sign. Okay. But for now, let's focus on the discrete. It's easier to visualize that. So probability mass function is the probability that random variable x is equal to the little value x or k, any value. For example, for tossing a coin, we talk about the random variable. We map head to 0 and tail to, let's say, 1. This is, let's say, head. This is tail. Doesn't matter which way you like. And then probability that x is equal to 0, probability in a fair point, probability that we get a head is 1/2, probability that we get a tail also is 1/2. When you roll a dice, probability that you get 1, right, is 1/6, the fair die. And then you get 6 also is 1/6, so probability all of them is equal to 1/6, right? So you can actually show it like this, the probability as a vector 1/6, 1/6 transpose. See? It's a multinomial, you can show it as a vector, right? So here I show it as a column vector. Okay, that's all we need to know about the expectation. Now there is a concept that measures the variability or dispersion with respect to the mean. Is called variance. It's widely used and it's a very important concept. So variance is usually denoted by a symbol sigma x squared. It's denoted by variance of x and is defined as follows: the difference between each element of x and the mean square, right? So variance is a positive quantity, right? So you square that. Expected value of x minus mu of x square. If x is a continuous random variable, we have a definition for expectation. So variance. So take this one as like a u. Expected value of u is u times the PDF of u or the PMF of u. So here is the same thing, is equal to the x minus mu x squared, this argument times the PDF of x. Right. So in general, expected value of g of x is equal to g of x times the PDF. Okay, it's a more continuous. For discrete, just change the summation to the integration to summation. Now, when you have x is a discrete, you get x minus mu x squared times the PMF, the probability that x is equal to little x or k, right? Okay, so this is this. Now, if you expand this term, let me just call it 1. If you expand this one, you get another definition for variance. What I mean by that, if you get x minus mu of x squared, if you calculate this one, you get 1, you get expected value of x squared plus mu of x squared minus 2x mu of x. So you get expected value of x squared. Now mu is a number, is a deterministic number because we already sum over all the values of this random variable is the average. So this will out of the expectation. Remember the mu is again deterministic. You get 2 mu of x, expected value of x. Expected value of x is again mu of x. So you get expected value of x squared minus mu of x squared. It should be of is the average, it's the mu of. So this is the definition of the variance that is used a lot. Expected value of x squared minus expected value of x squared. Okay? And the standard deviation is nothing but the square root of the variance, right? So you define the standard deviation as the square root of this variance. So usually when you want to compute the standard deviation, you start from the variance and then you take a square root. It's easier. Okay, now we talk about this in the context of random variable. Now if you have a vector, right, x1, x2 all the way to xn, right? So you can consider the weight of each component to be 1 over n. Think of it like that. You have no reason to put x2 over x1 unless you're otherwise told, right? So weight of each component, take it to be 1 over n. Therefore, define the mean or average as the same thing as an expected value. So you see that, for example, in a basic algebra class, define them, or basic statistics class, define mu or average. Usually is a notation in many linear algebra textbook. Average of x is sum of the element of x divided by n. But let's look at this expected value and see how we can relate it to that. If you go ahead in the definition of this expected value here, we said for now, sorry, let's focus on the discrete case, this one. If you set the PMF, the probability mass function, to be equal to 1 over n for all of them, we have n of them, right? They have to sum up to 1, right? The probability. So each one is going to be 1 over n. So if you change the PMF to 1 over n, you get 1 over n. What do you get? You get 1 over n sigma xi. You see that's going to be the average that we have for this case, right? So the PMF is going to be 1 over n. So you can see that you can map the expected value for a vector to be this. What I define top would be the general case for anything, right? You can say that the second component is more likely to happen. Here we assume that all of them are equal likely. Good. Now you see that the definition of the variance sometimes is defined as follows: as 1 over n, the norm of x minus average of x times the one vector. Remember the one vector? What was the one vector? One vector was this 1, 1 all the way to 1, like this, right? Why is that? Because x is a vector. Average of x is just a number. You have to multiply by one vector in order to subtract this to dimension, in order to dimension to match, right? And this is a Euclidean norm as well. Is equal to the variance, the definition I have. But I said, what, why? Let's take a look at this. We can start from this definition. Let's start from this definition, right? We write x as it is, right? Mu is the expected value is equal to what? It's equal to average of x. Okay. Now you take an expected value of that. Therefore, you have to calculate this quantity for I from 1 to n squared 1 over n. Right? Expected value. Remember the PMF. They're all equal likely. Right? What was the definition of the expected value? The general is equal to sigma xi, p of x equal to xi. Look at it like that, right? So sigma xi. Now we have sigma xi. We will do this one as a I1 to n of xi minus average of x. This is sigma xi that we have, xi minus average of x. But then this PMF is changed to 1 over n. Great. So let's erase this one. Let's give some room here. We're going to have 1 over n. Then we're going to have x1. I'm going to write some component for you to see what I'm doing here. X squared x2 minus average of x squared all the way to xn minus average of x squared. Great. So what is this one? This is nothing but the Euclidean norm, right? Euclidean norm of x minus average of x times 1 square times 1 over n. So that's how they define the variance like that, with a note that Euclidean norm square is the sum of element xi square, I from 1 to 1, right? So think each of this one take as like a yi, right? It's going to be Euclidean norm of yi, right? Or Euclidean norm of y, which each component is x1 minus average of x2 minus average of x, and so on and so forth, right? So what is the point of, again, this vector 1? People might get confused. Remember, x is a vector, average of x is a number. You want to subtract the average of x from every component of x, right? What do I mean by that? We want to get something like this: x1 minus average of x, x2 minus average of x, and all the way to xn minus average of x, right? So this will achieve by vector 1, because it repeats the average of x across the column vector, right? Good. Now, in order, let me just create some room here. Or should I put this one, put it here? Okay, good. Now, I have some mapping here, right? In order, when you see this in the your textbook or in the problem, you can actually map them really fast. So let's create a section here. Make sure it's not really messy. Okay. So for the mapping, when you see expected value mu or expected value of x, you can replace it with the average of x to be 1 over n xi in a vector domain. In a vector domain, this is a random variable domain. This is a random variable. This is vector, right? Anytime average of x, you have some expression you derive in your probability class, go ahead and replace it there with 1 over n sigma xi. You have variance, expected value of x minus mu square, go ahead and replace it with this cell. You just prove with y. Why this is correct, right? 1 over n, norm of x minus average of x times 1 square. Euclidean norm. Good. Now, standard deviation, no worries. Standard deviation, the square root of this, you can just go ahead and replace it by the square root of that, 1 over n. Okay, good. Covariance. You see, in this numerical algebra textbook, you usually see this covariance. So the definition of like a Pearson correlation, I have it here, right? It's just going to be a new definition for you, or something that you haven't seen. You might get introduced to a Pearson correlation in the statistics class in a context of covariance of xy divided by a standard deviation of each random variable, right? So first, you will learn the definition of the covariance. Covariance is defined as follows: x minus mu x times y minus mu y, expected value of that. So in a sense, variance is a special definition of a covariance. So variance of x is just covariance of x and x. Covariance is a measure of linear variability of two random variables with respect to each other, right? The mean, the random variable, when you subtract the mean from them. So in a sense, you get a if you replace x with y, you get a covariance of you get a variance of a random variable. Okay, good. Now you have this. Let's see how we can take it to the vector domain. Let's start with first x minus mu of x. What is going to be x minus mu of x? Let's start from this. X minus mu of x becomes xi minus average of x. Xi is each component, right? Because we are summing over all the components, right? So y minus mu y minus mu, what do I mean by that, right? if you have a vector, it's gonna be this. Each component is gonna be this. Each component. Right, each component. When you write in vector domain, that's why you get y minus average of y times 1. But each component, because we are summing over the component, we are writing component points. Right? So when you use the expected value, you use this summation I from 1 to n. We just talked about that. Instead of PMF, we just use 1 over n. Right? And each component is xi minus mu of x, average of x, times by I minus average of y. Okay, good. What is this? Forget about the 1 over n. What is this? What is it similar to? We discussed in the last video. This is the dot product. This is the dot product of x minus average of x times 1, because we also have to talk about the vector, dot product of two vector, and y minus of average of y times 1, right? So you can write it like this, and then 1 over n carry. So this is the definition of the covariance. This is the final definition that you have for the covariance. In a random variable case, it's defined like this. In the vector domain, it's defined like that. Anytime you have the covariance, you know the definition, you can just switch it very fast to the random, to the vector case. Okay. Now let's talk about the correlation coefficient, Pearson correlation, measure of linear correlation between two vector or two random variable. It's defined as a covariance of x and y and divided by standard deviation of each. So it's unitless, it doesn't have a unit, right? Now, we know the standard deviation definition, we know the covariance. So on the top, you will write the definition. I will tell you why there is no 1 over n. So first you write 1 over n, you copy this definition that we have here for a covariance here. A standard deviation, guess what, we have it. A standard deviation of x is this, we define it here. 1 over n, 1 over the square root of n times x minus average of x. So you have 1 over the square root of n for x term and 1 over the square root of term for y term for this standard deviation. When you multiply them out, you get 1 over n. That's why this 1 over n does not exist, because they cancel out the numeric and denominator. Right? So this is going to be the mapping between the Pearson correlation in the random variable domain to the vector domain. Okay? So if you know one of them very well, you can just immediately map between random variable and the vector. Okay, this is gonna help us a lot in the next video when we talk about actually the norm RMS values and this correlation angles and everything. Okay, so that's it for this video. Thank you so much for watching. See you guys all in the next video. Thank you.